Hi! During the next set of classes, we are going to show several optimizations that are possible when implementing an application on an FPGA-based system through SDAccel. Optimization can be applied at different levels. In particular, we refer to interface optimization, to improve the data transfer between the host system and the FPGA, host optimizations that concern the software code running on the host system, kernel optimization to exploit efficiently the FPGA resources. Within this class, we are going to focus on interface optimizations. Nevertheless, before diving into the interface optimization details, it's important to understand what are the key components involved in a typical system targeted by the SDAccel design flow. For this purpose, let's consider the key component of an Amazon EC2 F1-2X large instance, which is a cloud-based instance equipped with Xilinx UltraScale plus FPGA. This is a very representative example of a typical architecture targeted by SDAccel design flow. As we can see, the system is divided into two main parts. We have the host system and the FPGA board. The host comprises a general-purpose processor and the host DDR memory, which can be used for performing standard software computations. On the other hand, the FPGA boards feature the actual FPGA device that can be leveraged for accelerating our target kernel function and an onboard DDR memory, also referred as device memory in OpenCL terminology, that can be accessed directly by the FPGA device. The host system and the FPGA device communicate via PCI Express. In particular, with regard to an Amazon EC2 F1 instance, we have a third-generation 16-lanes PCI Express, which is able to achieve a theoretical bandwidth in the order of 16 GB per second in both directions. The FPGA resources are logically divided into a static region and a reconfigurable region. The static region, also referred as shell, contains the PCI Express and DMA controller to interface the host system and the memory controller to access the dedicated onboard DDR memory. Furthermore, the static region also provides Xe4 ports to interface the accelerated kernel function within the reconfigurable region. It's important to notice that the static region does not vary between different designs, while all the user logic is contained in the reconfigurable region. Through the PCI Express bus, and thanks to the static region on the FPGA device, the host can write and read data to and from the onboard DDR memory, and can also send control commands to the kernel function via the AXI-Lite interface. On the other side, the kernel function can read and write data to the onboard DDR memory by exploiting the AXI master-slave interfaces toward the static region, which are routed to the memory controller interfacing with the onboard DDR memory. Overall, the life cycle of an SDAccel application follows the following steps. First, after having initialized the OpenCL runtime, the host system loads a complete bitstream to the FPGA device in order to configure both the static region and the reconfigurable region that hosts the accelerated kernel function. Second, the host copies the input data from the host DDR memory to the onboard DDR memory via PCI Express. Third, the host configures the kernel parameters and starts the kernel execution via the AXI-Lite control interface. Fourth, the kernel starts the computation. It reads and writes data to the board DDR memory via the AXI master-slave interface that are connected to the memory controller. Notice that the kernel is free to use the onboard memory as needed and can read and write multiple times during execution. Fifth, the kernel completes the execution and notifies the host. Sixth, the host copies back the output data generated by the kernel from the onboard DDR memory to the host DDR memory and continues processing as needed. This is the basic execution model of an SDAccel application. Nevertheless, depending on the application, variations of these models are also possible. As an example, instead of reading back the data to the host upon kernel completion, the host might load a different kernel on the FPGA partial reconfigurable region and process the data generated by the previous kernel directly from the onboard memory. In this fashion, it is possible to minimize the number of memory transfers to and from the PCI bus and to read back the data only when strictly needed. Additionally, in the previous example and while describing the architecture, we considered a single kernel function. Nevertheless, SDAccel also allows to instantiate in the same design multiple kernels, which can be either duplicates of the same kernel or completely different kernel functions. Then, thanks to the OpenCL runtime, the interaction with the different kernels is transparent and the host is free to assign different input and output buffer to each kernel. In order to achieve efficient data transfer throughout the execution of the application, it's necessary to maximize both the PCI Express and the DDR bandwidth. Even though the PCI Express bandwidth and overhead vary sensibly according to the amount of data being transferred, its interface is fixed. On the other hand, the communication between the kernel and the onboard DDR memory can often severely reduce the performance of the entire system if not properly optimized. Indeed, the AXI master-slave interfaces are not fixed and the data width of the interface depends on how the kernel function is implemented. Additionally, if the kernel performs many small memory accesses to the DDR memory, the overhead incurred by each transaction might easily jeopardize the acceleration efforts. Due to this reason, here we mainly focus on optimization related to the AXI master-slave interface towards the DDR memory, while we will return on PCI Express bandwidth maximization when discussing the optimization related to the host, since it's the one responsible for performing the data transfer on the PCI bus.